Hey guys, welcome to Safi Mixed. In this video, I will answer the question, what is derivative? Or in other words, I will build the concepts of derivative and will derive the relation for the definition of derivative. However, coming to this end, I first want to add a comment on the importance of derivative. The derivative of a function is very important quantities in all branches of theoretical sciences, and it helps us to construct models for solving problems of practical interest, and it also helps us to build new theories in physical sciences. And in developing the concept of derivative, it is suggestive to use geometrical approaches instead of analytical approaches. So to this end, it is further easier to use a plane geometry. So to this end, I consider a plane and the ordinates could be any physical quantities. For example, the horizontal axis could be time, velocity, position, angular displacement, or any other physical quantity. Similarly, the vertical axis could be velocity, acceleration, force, energy, or any angular momentum or anything else could be written along the vertical axis. However, to develop the concept, I would take the easy way. I would just represent the horizontal axis with position x and the vertical axis with position y. This means we are dealing with the trajectory of particle or with the path of the particle. And when written in this form, that means that the vertical position of the particle depends on the horizontal position. There is a link between the two positions. And this link is generally written in the form of function, that is, we write y is a function of x. And remember, this function could be anything, like it could be a linear dependency on the position, or it could be quadratic, for example, in the case of parabola, or this could be sinusoidal, like in the case of simple harmonic, where the position of the particle depends on sine of the theta with the vertical or equilibrium position. So we, in fact, don't need to worry about the form of this function. It could be exponential, logarithm, or any combination of those functions and more complex analysis. And present, only the geometry of this function is sufficient to explain the concept of derivative. And for that purpose, I take a curve in this plane like this. So this curve describes the path of the particle for the time being. And in order to study the behavior of the function on this curve, I just take 2 points on the curve. One this point, and I represent this point with P, and one this point, and I represent this point with Q. Then I want to assign the value of the coordinates to point P, and that I can do by dropping a perpendicular from the point on the horizontal axis, and I write that point as x sub 1. And similarly, I drop a perpendicular on the y-axis, and I represent that with y sub 1. I would mostly call x sub 1 as x1 and y sub 1 as y1. And then the coordinates of P are x1 and y1. And the same I can do for point Q, and I represent the position along x-axis with x2 and the position along y-axis with y2. So the coordinates of point P can be written as x2, y2. Now, the change in the values of the function between these 2 points is in fact delta y equals y2 minus y1, or in terms of function, I can write that as f x2 for y2 minus f x1 for y1. And this change in function corresponds to the change in the dependent variable. Okay, let me call the variable that we take along x-axis is called independent variable, and the function that we take along y-axis is called dependent variable. So the change in the function in fact corresponds to the change in the values of the dependent variable, and I write that change in the form delta x equals x2 minus x1. I call this equation 1 and this one equation 2. Now, what if I divide equation 1 with equation 2? That is, what if I construct the ratio delta y over delta x? Then the right side of the equation just become f of x2 minus f of x1 divided by x2 minus x1. Let me call this equation 3. Okay, the right side of equation 3 is in fact the change in the value of the function per unit change in the value of the independent variable. In other words, the right side of equation 3 gives the rate of change in the value of the function with respect to the value in the independent variable. And if I look to the left side, and you recall from your courses in calculus, delta y is in fact the res and delta x is the run. So res over run by definition is slope. That means delta y over delta x defines slope. But slope of what? Slope of the line joining point P to point Q, a line like this. Let me call this line L1. This is obviously a secant line. That's all right. Equation 3 now in fact provides the information about the slope of the line. And this is a single piece of information, very limited, say very little about the curve. This equation is unable to differentiate between the curves, rather I would say between the infinite number of curves that pass through two points P and Q. For example, if I take a curve like this, then I take a curve like this. This curve passes through the same 2 points. This one curve passes through the same 2 points, and the curve of the solid line passes through the same 2 points. So this equation is in fact unable to differentiate between all these 3 curves, and obviously I can draw other infinite number of curves in this area. I can take a curve even like this. For this curve, even this line L1 provides the same information. So equation 3 is a good equation, but it is unable to differentiate between the infinite number of curves that are passing through point P and Q. Or in other words, the information provided by equation 3 is very limited. What should I do if I want to get the information about every point of this curve? Yeah, I can play with this equation. Instead of writing in this form, I want to write a dynamical form of the equation. So I write equation 2 in the form x2 minus x1 equals h, or I can write x2 equals h plus x1. In fact, I am parameterizing equation 2 in terms of h, where h provides certain values along the independent variable. So if I use this value of x2 in equation 3, I can rewrite equation 3 into the form delta y over delta x equals f of x1 plus h minus f of x1 divided by h, and I call this equation 4. Equation 4 is richer than equation 3 in a sense that it provides large number information for different points of the curve. Let's see this. How can I do that? What if I take the midpoint of these 2 points and I drop a perpendicular like this, then this is another point which is joining these 2 points. You see, when I reduce the value of h, because now h is the values along this axis, I'm getting closer to point P, and h now provides the information or the slope of this line. And if I further reduce the value of h, like the mid of this, I reach to this point, and now I have the slope of this line passing through this point and this point. This is line L2, this is line L3, and so on. So if I keep on going and reducing the value of h, what will happen? I will finally reach to a point very, very closer to P, and that would be a line like this, L5. L5 is no more a second line. If I keep on getting closer and closer to x1, that means I'm reducing the value of h. So if h is very, very small, we are moving over the curve, or we are moving, or we are shifting from a second line to a tangent line. Analytically, this thing is obtained, we know from our courses in calculus, by taking limit of this equation. That is, if I take the limit of this equation such that h tends to 0, then geometrically we see that when the value of h is decreasing, we are shifting from a secant line to a tangent line, and then this thing become delta x equal to limit h tends to 0 f of x1 plus h minus f of x1 divided by h. I call this equation 5. Now equation 5 is very rich in providing the information, because equation 5 traces the curve for each value of h. If we gradually increase the value of h from 0 to in uniform steps, we will be tracing this whole curve. For example, I take h first to this point, I'll move from this point to this point, then I increase the h to this point, I move to this point, and so on. Keep on increasing the value of h in uniform steps, we will be able to trace the whole curve. That means this thing provides the information of the behavior of the function over the whole curve. So this is very important. Such behavior of functions are everywhere in theoretical sciences, in engineering, in chemistry. In order to understand the behavior of a function for every possible value of the independent variable, this equation is very important. It provides that thing. It provides the information of the function for all possible values of the independent parameter in terms of h. So this equation is everywhere. Therefore, being ubiquitous and very important, the the left side of equation 5 is redefined, and it is written in the form limit h tends to 0, delta y over delta x is written usually as d f of x over dx. Sometimes it is further abbreviated by writing this f of x and putting a prime over it. So f of df of x over dx, or f prime of x, is in fact the derivative of the function f, which is defined through this one equation, the limit of this whole thing. So equation 5 in fact provides the definition of the derivative of a function. And if I want to define this in words, the derivative of a function is the change in the value of the function with respect to infinitesimal change in the values of the independent variable x, which I am writing here in terms of h. One more thing, when the derivative of a function is taken with respect to a time, then a common notation for that is f of x, and we put, instead of prime, we put a dot over it. So a dot where a function would represent the derivative with respect to time, or I would then write this as f of t. So the derivative of a function with respect to time is generally written as putting a dot over the function, and the derivative of a function with respect to position is written by putting a prime over it. Now, if we take velocity along this axis, then this will be time, and the curve would then be the rate of change of velocity and would define the acceleration, or the curve would provide the information about the acceleration of the particle. Similarly, if this is t and this is position, then the curve in the plane would provide information about the velocity of the particle. So that's why I said in the beginning of this lecture that this ordinate could be time, could be position, could be any other physical quantity. So I will use this definition of derivative, that is, in general, we write the derivative of a function f prime of x equals df of x divided by dx equals limit h tends to 0 f of x plus h, that is, I'm now dropping the subscript from x, minus f of x divided by h. So I would suggest to memorize this definition of the derivative, because I will use this definition in the coming videos to build the rules, to build the different rules for differentiation of function of different kinds. At the end, if you haven't just subscribed to Safi Mix, kindly support the channel by pressing the subscribe button and also the like button on the video. Thanks for watching.